Okay, we're recording. Welcome to Lecture 11. Last time we went in great detail over TCP windowing, and I'm listening to see if you guys will need more help as you get into the homework. I have a big block of time for the first time in weeks, thanks in part to daylight saving time having already happened there, but not here. So it's 7:30 where I'm at. So I have an extra hour to kind of crank it out. And what I'll be giving you are some things on TCP windowing. So please do let me know if you feel unprepared for it or if you're confused by it, because it's pretty much the core of networking. So I need to make sure we spend the amount of time necessary for that to be, for you to have a chance to become comfortable with it. You will have to work at it, but there's tons of other stuff out on the internet about it as well, including animations and spreadsheets and presentations and lectures, and some of them are fantastic. So you should have a good experience getting through this. What we're going to cover today is quite a bit of Chapter 4. In fact, we'll get up to addressing. We'll get into the Internet Protocol itself through fragmentation, and depending on how things go, that is likely where we will stop. So the reason why the 7th edition of this textbook exists because they split this layer of TCP/IP into 2 chapters. And logically, there are 2 things that go on in the network layer, at least if you think about what happens inside of a router. You have the data plane, which is the part of the router that has the responsibility for actually forwarding the bits that are coming in one input port and getting them out of an output port. So as data comes flying into your router, something's got to actually figure out, how do I get it out of whichever port's coming in? And this is a zoo because there's stuff coming in all of the ports at the same time. So you have to have a switch that's not just fast enough to handle the bandwidth of one of these, but fast enough to handle the bandwidth of all of them. So that separates the wheat from the chaff pretty quickly in the industry, and it's caused lots of companies to disappear that can't keep up with the huge demand of processing required in environments like massive data centers, cloud scale computing. And that's where the money is. So that's where a lot of the attention is built, it's where a lot of the innovation is built. And it's also where TCP turns out to be not so much frail, but pushed to the limits. And so there's been some changes. And we talked a little bit about that in the last chapter as well. The other part of what goes on in this chapter and in a router is the decision making. Like, well, you're going to decide to send something over here from this input port to that output port. Well, says who? Who knew to do that? It's very likely the case that you've got these networks out here, and there's probably lots and lots of ways of getting things from one site to the other. And so, why did you decide that one over the other one? And that's the responsibility of essentially mapping algorithms that Waze also uses to figure out which way to tell you to go. And so it's very similar to other kinds of networks that you see, which way a plane should go, how often a train should leave, which way you should go with the mail truck to shorten your route, et cetera. So we're going to talk about what goes on there, but it is an independent topic largely. And so there's a big move to split that out of the router and move it into the data center environment and take all of that decision making and just leave the router to do the switching part. So we'll talk about that. And we're going to start by looking at sort of what's inside of a router as well. And as you guys saw from the slideshow on the Nexus 7702 switch, there's less inside of the router when I get done with it than there was when we started, because I tend to disassemble things. It reminded me, after I talked to you guys about that I remember when I was 12 years old, I wandered through the woods and came across a motorcycle that belonged to someone. It was actually in their backyard, except there was no fence, and took it completely apart. And I came home, and my dad said, well, the neighbors saw you do it, and they're totally okay with you taking it apart. I got really nervous that they were going to come out and yell at me when I heard that they saw me, and he said, they just want you to go and put it back together. And I will tell you, it's a lot harder to do that, as I also proved with the Nexus switch. So we'll try to disassemble things in a non-destructive fashion if we can, but there's there's no reason in the world why, if you've got an old router or something like that around, like from the phone company or something, you should rip that thing apart. Just tear into it and figure out sort of what's going on. Okay, so we're going to understand the services that this network layer is tasked with providing. What kinds of things is it responsible for doing? We'll make sure we have a very clear understanding of the difference between forwarding and routing, or switching and building your routing table, or some other euphemisms for it as well. And we'll look at how routers work today and where they're headed, because there is that shift that's going on. And we'll introduce this idea that I think is going to take over the way we manufacture equipment in this industry, in this area of generalized forwarding. And of course, the best example we have to look at is the internet, but we will vary from that quite a bit, because lots of things that you will want to do, that your company will want to do, your employer, can't be done on the internet. They can be done in routers, and they can be done with the same software, but most of those features are turned off for the internet to work. And so we'll spend some time exploring those things as well. So the idea of the network layer is to get things from one device to the next. And it's the first layer we've looked at, having started at application and moved down to transport, and now we're at network, where you've got every device from end to end that runs this layer. So all the routers from one end of this to the other all run the network layer. So here's the first time where we're really worried about hop to hop to hop. With the transport layer, it only ran in the computers at either end. So you were responsible just for making sure the transport layer was sending messages that were intended to be interpreted only by the transport layer at the other end, and they would hand them down to the network layer to be sent hop by hop, and that's the layer we're at now. So on the sending side, you have this idea that started at the top, where you take your information and you put it inside of an envelope, and you add to the outside of that envelope whatever addressing and other features might be needed to handle the additional responsibilities that you've got. So for example, if it's a DHL or a Federal Express envelope, at some point it may go into a silver container in the belly of a plane, and the address that goes on outside of that is totally a different nomenclature than what goes on the individual envelopes. It's a 3-letter airport code, and it's got probably some funky looking barcode things on it and stuff like that. Yes, it's part of the same process, but the mechanisms and the things it adds are different. It put them in a metal container, not a paper envelope, and it doesn't have a little pouch on the side. It has big giant stickers, and it goes in a plane, not in a box, and things like that. So we're busy doing that as well in the internet, and the analogy that is suggested by the name that we use for this is not so much putting things in envelopes, but maybe putting things in capsules, like little grains of medicine for like a headache reliever that go inside of a plastic Tylenol capsule, for example. So we call this encapsulation. So just think about putting things in a capsule and then putting that in a bigger one, and et cetera. On the receiving side, you strip this stuff off. You inspect things as you do it to make sure, did that metal box in the belly of a plane land at the right airport? Is it at the right city? Do I need to continue by putting it on a truck now and continue its journey? Do I take everything out of the metal box? So that problem of figuring out what to do at each step is very similar to this layered process that we have going on here. So what the router does is it looks at the fields in the datagrams that are passing through it, and generally, and this is changing, but generally you only care about one field, and that's the destination IP address. There's lots of other things in the header. We've seen that, but we're generally concerned with just that one. Okay, so there's an animation, but it's supremely uninteresting, but I'll try to show it to you anyway. It just basically shows things moving their way through this router by router. So the network layer lives in all these devices. So at some point here, this green thing just goes nuts, and it's impossible to kind of follow what in the world is going on. But it's basically showing you every device along the way stops to look at the network layer, picks it up off of one data link, throws that data link wrapper away, exposing just the network datagram that remains. It now can see at the beginning of that datagram the addresses, and it makes a decision on which port it needs to go to next. That port is attached to a network. That network has a particular data link technology, Ethernet or Wi-Fi or something like that, and it will rebundle up the datagram that's at requires. Since we mostly use Ethernet and Wi-Fi, and they're both part of the IEEE 802 standard, they mercifully use lots of similar things like the size of addresses and the range of addresses and the size of frames and things like that, just to keep us from having to learn things from scratch. But unfortunately, kind of gives it gives the illusion that, or the impression that, all data link layers work that way, and they most certainly do not. We just happen to use two, the most popular two that do. But if you get further into a network, one hop past what you're doing, you'll find everything changes. We're not using that everywhere in the core all the time of the network. Okay, so moving along past that, two key functions that we talked about were forwarding and routing. So the forwarding is the act of moving things through. But I like to go backwards on this slide because it makes more sense. What was it that Eisenhower said about D-Day? Plans are nothing, planning is everything. So routers build plans, but they're constantly planning. They're constantly exchanging data with their neighbors, with routers that they can directly connect with on LANs to which their own ports connect, and exchanging data with them on the other networks further away that each of them can see, and therefore that each might be able to help the other one reach. And so this cascades its way through a network. So at time one, you may exchange data with the people that you can see, and they are busy doing the same thing with their neighbors as well. They learn things from their neighbors during the same time you're learning things from them and exchanging. And so by time two, if you just let them continue to exchange, by the second round of time, you will have learned what's two layers away because it's made its way here, and now it can make its way all the way, the rest of the way. Let me turn off my notifications. Okay. And then the third round and the fourth round and so on. So this gets old after a while because on the internet it could be, I don't know, tens of thousands around. You don't want to wait 5,000 minutes for your network to build a map, and plus the network is changing while this is going on, and so it's just a constant task of updating. Again, imagine what Waze is going through. It's constantly receiving new data. It's constantly doing things. It may reroute you in the middle of a trip. Thank goodness for Waze, because it's made conceptually explaining what's happening a little bit easier. All right, so routing algorithms are programs that run inside the router, and they have the responsibility of setting the rules for exchanging this information, building the packets that will be sent to the neighboring routers, setting the time frame and the frequency with which it's going to be done, and deciding what to do with the info when they learn it. So if you learn that this has gotten a little bit slower than this, is it time to switch to this one, or is this one still better? So there's interesting rules that we'll look at when we get into the routing protocols themselves, but this is definitely the realm of secret sauce, where there's lots of proprietary work that's done. This is total computer science in this area, graphing and algorithms to find the shortest paths and figuring out how often you should react to changes. So for example, if the speed on the on-ramp on 45 goes to 0 all of a sudden, and it had been 30 kilometers, do you just like instantly reroute everyone away from it? Or do you bide your time a little bit because maybe just somebody stopped for a minute to change a tire or pull off the road for a moment? Or maybe somebody bumped into someone, they're going to get out and look and go like, no big deal, and continue on their way. So you have to be careful in routing, especially not to overreact to bad news. So as we'll see, there's this concept that good news travels fast, but bad news takes a long time to get there. So what that basically means is if this link became suddenly slower than this one, before you start moving everything over here, you might just wait a second. Maybe this router rebooted. Maybe there was a hiccup on this network. Maybe it's just fleeting, a problem. Most of the time, that's what's going on. So you've got to, as a computer scientist, figure out how to take that into account. So you really have to understand the behavior of the network technology that you're working with. What are its characteristics? Is it prone to doing things like that? How often do those things happen? What's the distribution? Am I better off switching or not? It has an impact on the buffer sizes you have in your routers. It could cause more things to get dropped. So it's a fascinating field, and lots of people work on it. So that's the routing, determining the route. So just like a trip, before you make a trip to someplace else, let's say it's a spring break trip, maybe you start off by taking the light rail downtown, and then you're going to catch a bus out west to Katy, and there you're going to hop in the car with a buddy of yours. You guys are going to then drive down to the Rio Grande Valley and or maybe Padre Island, and you'll take a ferry across, on and on and on you go. Right? So different modes, but you're going to plan the thing out. And then forwarding is the actual act of executing on that plan. So inside of a router, what every routing protocol's responsibility for generating is a routing table. It's a list of the decisions. If you're asked to go here, then take this route. If you're asked to go here, take this route. If you're asked to go here, then leave the router out of this physical port. So that table is constantly being updated and pushed into the part of the router that is got the responsibility for actually moving the bits from one side to the other. I'm so tempted to say physically move the bits, but as Nicholas Negroponte said once to me, who helped found Wired and was from the MIT Media Lab, he goes, Kevin, it's bits, not atoms. So I'm like, okay. So forwarding is the act of moving these things around, and that's also where a lot of proprietary work gets done. Those ASIC chips that had the Cisco name on them, when I peeled off that heat adhesive, that heat passive adhesive that I showed you in the Nexus photos last time or two, that's where the switching decisions can get made, and the switching can actually happen is with the help of things like that. But so that device was a switch. That device was a very high-speed device that can move things quickly through from one input port to an output port. So here's a different look at it. The data plane happens in every single router. There's no way to pull that out and centralize it someplace else. This is where the bits arrive, and this is where you need to make a decision. So it's like showing up at the intersection, and it's just, how are you going to actually get the person off of 59 Southwest Freeway inbound to 610 North past the Galleria. So that's the task of doing that, and it's essentially a function of forwarding a packet from an input port to an output port. Fortunately, we put the destination addresses near the beginning of these streams of bits. So the packet, of course, shows up bit by bit, starting with the first one. And we want to take a look at it as early as we can so we can get a jump on making a decision on where it needs to go, so that by the time the whole packet has arrived and we've been able to complete our error checking to make sure it hasn't gotten corrupted along the way, we have also been, in parallel to that, looking through our routing table to decide where we want to send this thing. And we've made that decision. We've also done some other things in that time, like figure out, is the destination available? Is there room in the buffer for that output port? Is somebody else trying to send something to that output port right now? Things that might slow me up. In fact, things that might cause me to change the order of things that are in my input queue. So I just got a packet going to A, and right behind it was a packet going to B. I might move B up to the front because I have a clear path to B, and I don't have one to A right now. Maybe it's busy. The control plane is ideally thought of as a network-wide algorithm. Again, back to Waze. You want Waze to understand what's going on across the entire area so that it sends you in the right direction first. It may be completely non-intuitive that you want to go left instead of right, when where you're trying to get to is actually kind of in the direction to the right. But if it's far enough away and there's things going on, it might be best for you to start off with a little bit of a detour to cut your total travel time. So that requires knowledge of what's going on well beyond the inside of your router. And this turns out to be a very profound challenge for internetworking, because on the internet, it's never possible to have a completely comprehensive view. Nor do we really need it, obviously, or else the internet wouldn't work. So you just got to remind yourself that if we've lived with it without it for this long and things are working okay, they must be able to work okay. But there's a lot of interest in expanding the scale and the scope of your knowledge of what's going on beyond just your immediate vicinity, so you can make better overall routing decisions and maybe shift traffic this afternoon from Northern Europe down for the United States through South America, because there's some undersea fiber that's more available. Even though it may add more latency, it cuts down on buffer delay. And that would not be intuitive, but that's only something you can do if you've got kind of a higher level view. So there's a move to pull all this stuff out away from the routers and take it away from them and move it into a data center. And like we've talked about before, the part of the router that does what you now know is the control plane. It's just an Intel-based server running Linux, running programs written in C or Python or some other language like that. Well, I have devices that can do that in a data center as well, and they cost a whole lot less because whereas the program running on the router might be idle part of the time and it's just wasting that asset, the data center managers are really good at making sure they're keeping those things busy so that my share of having to pay for that server is less and less and less if I can share the cost with other people. So that's what's driving the cost down inside the data centers, and that's why we want to move applications that we can run there to there. There's that natural gravity of pulling things into where the costs are lower. So that's shown on this slide in these last two bullets. So traditional routing algorithms are implemented inside the routers, and what we call this concept of taking these programs and moving them up into a data center and letting the model of what's going on happen just purely in software is defining your network with programs only, software-defined networking. So if you rip that stuff out of the router, then it leaves you with an important communication gap. And the problem is you're going to still need to communicate. So we're going to build up to that. So first of all, the per router control plane, it is still split into two conceptual areas, the control plane and the data plane. But here a routing algorithm is running inside of each router, and they're exchanging data furiously with each other. So if you ever have an entire network go down like 100 routers in a building, and because the power goes off, like hard off, and you turn it back on, your traffic is going to be dominated on your network for the first minute or so by the routers all exchanging data with each other, assuming they don't just statically code the last thing they do. Right? So there's lots of exchange that goes on. Down at the bottom, they are pushing what they're deciding. They're making decisions with these routing algorithms, and what they're building are routing tables. The output of every routing algorithm is to produce one of these tables. And that table is the only thing that separates a working switch from a non-working one. You have to have this table to push down into the forwarding part of this router so it knows when it receives a datagram that has an address that it's trying to reach, you look through your table to figure out, do I have a rule for that? And if so, you send it where you're told. Out port 1, out port 2, or out port 3 in the case of the one that we see down below. So logically, they're separated. What we basically do with software-defined networking is extract that top part and build those tables instead inside of a data center, where maybe inside of one server, we can repeat what we had been doing in 200-300 routers and dramatically reduce the cost. So this is the direction that the industry is moving. This is where the place I work, Cisco, is moving to very aggressively, and there are some customers who are way ahead of others. This is interesting phenomenon, and I have to think more about, if I see this, if I believe I see this all the time with new technologies, or if this is as it feels like quite unusual. And what I'm talking about is there's one carrier, AT&T, who has leapfrogged, just raced ahead with this concept of software-defined networking to the point where they're the ones writing the textbooks and building the first university classes and things like that. And a buddy of mine sent me the textbook from AT&T, and it was kind of cool, a little nostalgic, but the people that wrote the chapters, I worked with them. I knew them. So I had moved over to Cisco by the time this sort of took root. It was maybe in conversation, but it was a dream still when I was there. But 80+%, 85, maybe 90% of their network is now built this way, and it has lots of rewards for them beyond just having things run in just a fewer number of servers. They actually can control everything going on in their network now from kind of a central location, which was heresy before. It's like impossible to do. When I had a customer that wanted a network to Hong Kong, that took months, not because we didn't have the circuits, but just working out the details and getting all of the all of the ports defined and getting the commands ready to issue and all the different languages that these devices spoke and just all the work orders. It was a huge amount of work. But now with this stuff happening, you can drag a connection icon over as the customer on a web browser, and thousands of instructions will be cranked out the back and make that happen in a matter of moments instead. So it's enabled much more versatile networking, and it's allowed customers to push things into data centers all around the world. We never thought maybe they would want to do that before until people like Amazon and Google came along, and now people want to put things in other people's data centers, which was not all that common. So back to the diagram. Now that I've extracted this stuff and I've put it into a data center, this control plane somewhere, I need some piece of software to stay behind, because what happened before is when something changed on the network, the router saw a link go down, for example, or it saw congestion building up. It just had to tap on the wall because the control plane was sitting right next to it. But now it's remote someplace else in the world. So this CA is a control agent. It's a program that will receive these alerts from the router about what's going on, these status messages, and push them up into the cloud. So it'll send them over the internet. And if there are inquiries that the remote controlling plane up here in the data center has for the routers, it can send queries down via this new API that was defined, and there's people competing for who's King Kong in that area. The winners have more or less been decided, but they'll push with this protocol, kind of like HTTP or SMTP or something else we learned. They'll push this protocol down to this control agent, which knows how to speak that, and then it will turn around and speak the specific language of the switching fabric that manufacturer's device uses. So there's a move to try and consolidate the languages, consolidate these APIs, and build much more genericized, compatible technology. So soon it might not matter whose name is on the switch. They will all speak the same 15 commands, plus maybe some extra ones as well. So this is very commonly done with SNMP, which is a network management protocol, where you can count on all devices responding to certain kinds of common messages, but they all have custom ones that they do as well. And it's heralded in this arena where you can buy a program like Service Desk, which is a $100,000, $200,000, $300,000 program, but it has all of the hooks to talk to every device you would ever see anywhere in a networked infrastructure, from the switches and routers to the automated door locks, the lighting systems, the air conditioning, the ventilation controls, the water purge pumps down in the underground conduits, badgery on and on, curtains in a data center room. Everything you can imagine, you can now control from one kind of panel. So at 7-Eleven in Dallas, for example, they have this software installed, and they monitor what's going on at all of their sites around the hemisphere, because there's tons of 7-Elevens outside of the U.S., north and south, and that's a key mechanism that makes it so that they can blend in a variety of manufacturers' equipment. So what we think is going to happen is we'll start seeing other manufacturers building just switches and ignoring anything having to do with the control plane. And they basically say, here's my switch, here's the ports I've got, plug things into me if you want, and then you can control me from someplace else, but you're not going to do it from here. So that's kind of the idea, and what companies that manufacture this gear today and have sold the software, they've been like mainframes in the past, where you bought the hardware from them, and then they also supplied the routing algorithm, the software, and they supplied all the network cards, and they supplied the maintenance. And if you wanted to learn how to program it, you took their classes that you paid them to teach, or you paid somebody else who's licensed it from them, and you basically became an expert just on that particular manufacturer. That's the way mainframes worked 50 years ago. And you never would buy a computer that way today. You might still decide you want to buy Intel, but even there's competition for them. So first you figure out the computer you want, you figure out who's selling it to you, then you can pick the operating system or systems that you want to run on top of it and the software you want on top of that, but they're all independent decisions. That is not the way routers have worked. So think of this as moving towards kind of an app store model for routers, where you buy the switch from someone, you decide what communication mechanism, what protocol you want to use to control it, who's going to write the CA code and the remote controller code, and so that's what you'll pick and you'll install. And then that switch manufacturer will support, of course, all the popular ones, and they will have already worked with those manufacturers. So if you tell them, you know, I've chosen this open software package to do this, then they'll say, okay, well, no problem. We've already worked with them, and they already have a little file. And if you just tell them that the model number I've got, they'll know everything they need to do. They'll know exactly what to tell me to reboot me. They'll know what to tell me to get me to add something to my routing table. They'll know what to tell me to get me to tell them what the status of all the network links are. All right, so a little bit of nitty-gritty detail on that, but that's super critical because this is the environment you're going to be walking into. You'll see it at the carriers first. We think you'll see it in educational institutions next, but the carriers surprised people by, I think, moving so quickly and into little variations. So I don't really know who's going to, kind of do it next, but definitely not going to get you a job if you know how to do it, because people are scrambling to get this implemented as fast as they can. But it will certainly impress a potential employer if they've heard about it, they're wondering about it, and they know that like you kind of conceptually understand what's going on. You might be able to help them put a plan together that gets them there. So what does the service model basically here mean? It's a way of defining what it is you need this layer to perform for the other layers above and below. What services is it going to provide? Why does this layer exist? And examples of things that a network layer could do with its service model is to do things like guarantee delivery or guarantee that a packet will get there within a certain amount of time. You can kind of think of FedEx in that example, or UPS. You might guarantee that things get done that way on sort of a per datagram basis, but then when you step back and you look at a flow of information, like a stream of packets, maybe you want to tell the user that you're going to take care of getting them there in order, and that you're going to guarantee them a certain amount of bandwidth. And then kind of the holy grail is that you're going to stay within certain limits for the spacing between packets. So if I send you packets that are spaced apart like this, and there's 4 here, you can get the 4 to me in the same total amount of time, but you can do it this way, or you can do it this way, or you can do it this way. And my guess is the user, if they care about a certain minimum amount of bandwidth, they're going to want it this last way. So this inter-packet spacing, when that changes, that's called jitter. How much jitter is there? And there's a measurement. The more jitter there is, the more prone packets are to having that spacing vary greatly between them. So you can decide that you want to tackle this, and your network implementation may want to offer that as a flow service for people. Carriers can do this. Institutional networks can sort of do this. They're not great at it sometimes. The internet cannot at all do this. So if we start with the internet as our example, it's purely a best effort service model. Give me a packet and we'll see what happens. That's basically all it can do. This is why TCP exists, because if you basically say, all right, every letter you give me, we'll just see what happens, then what your secretary might want to do is make a photocopy of that letter before they drop it in the mail. And if it doesn't make it to the other end, they have a copy and they can make another and send it and try until they finally come back and go, this letter is never going to make it there. Right? So that would be like TCP. There's no guarantee as far as packets not being lost. There's no guarantee that packets are going to stay in a certain order. There's no guarantee that this inter-packet timing is going to be maintained. There's also no congestion feedback exactly, although we talked about explicit congestion notification, and when we talk about ICMP, we may get a chance to talk about source quench messages, and both of those are exceptions to this claim that it's just a no. But even beyond that, TCP has the ability to sort of infer that packets are being dropped by things like not getting acknowledgments back, for example. Okay, the other side of the world, though, the other part of this network is the carrier side, and they absolutely have lots of technologies to do all of these things, to give you all kinds of variations and options. And again, ATM is a great example of a service model. They offer a constant bitrate model where you pay a premium, but you're guaranteed a constant bitrate. So they will hold other people's packets back to make sure they give you yours. And they'll also engineer their network to have a higher assumption of how busy you're going to be, because they can absolutely count on you paying for that bandwidth, and so they're going to build that bandwidth for you. And they're not going to make other people compete with you for that. There's variable bandwidth, adjustable bandwidth, and then unspecified, or people use different names for these things, but almost everyone goes by the acronyms, CBR, VBR, ABR, and they also mean different things with different network technologies. But the ATM nomenclature kind of caught on, right? So this unspecified one at the bottom is similar to what the internet does. But they do still guarantee that things are going to arrive in order, which the internet cannot. So when you enter the workforce, if you do that, and you are looking at how to kind of design a network, you have lots of technologies like this that you can implement at the network layer that will allow you to offer different service models to different things, and you will want to do it. So if you are going to do voice over IP across your entire network using someone's VoIP phones, then that might be an area where you want some constant bit rate to maintain at least 5 calls simultaneously going between the main offices, and then maybe you want to also tack on some variable bit rate where the chances are 80% that you'll be able to do up to 5 more calls, and then after that, I might just tell you you can't make the call right now, or who knows. But you're going to want these kinds of tools. Other examples out there are just plain old Ethernet that can be added to a network service model, although it's layer 2. MPLS, the same kind of thing. We'll see other examples as well. All right, so what's inside of a router? Input cards and output cards, a high-speed switching fabric, or if you spell it like the author did, how many years have I not noticed that? A high-speed switching fabric, and then your routing processor. So the control plane is up at the top. The forwarding plane is down at the bottom. The control plane can react to things and change routing tables in milliseconds, but it's software. It's running on an Intel server. Down at the bottom, you're running orders of magnitude faster than that, 3 to 4 to 5 orders of magnitude, picoseconds, nanoseconds, etc. You don't have time to really do anything in software. So what you're never going to do is grab a packet that comes in off of an input port and then go and ask the software what it thinks you ought to do with it. You have no time. You are thousands, tens, or hundreds of thousands of packets per second too slow to get that done. So what are we going to do? Well, remember the routing table, the one product that we produce out of the routing algorithms? That's going to have to get pushed down into the hardware, into firmware in every single input card. So you're going to have to arm each one of these input cards how to make its own decision on the fly for what to do. This would be like giving a soldier in the field all of the knowledge they need and the tools and the permission to make their own decision about what to do. They do not have time to call back to headquarters and figure out, this guy's running at me with this tank. What do you want me to do? Shoot it, right? So you want to give the tools out there so they can react very, very quickly. It's interesting because these tables can be 1 million lines long, and you need this firmware not to just implement the same type of sorting algorithm or search algorithm that you might deploy in software. Newton's approximation is not fast enough. Bubble sort is not fast enough. So what you need is a radically different approach. And we'll talk about the type of memory that we use to kind of get that done. So there's 3 things that are going on in these input cards. One is to terminate the type of media, whether it's an antenna that's pulling in bits arriving over a wireless connection like Wi-Fi or microwave connection, or maybe it's a copper connection that is looking for changes in voltages, and based on the technology, it's determining how to transform certain patterns to ones and zeros, or it could be something that has a light receiver and a set of mirrors that break colors out into their own individual spectra that will pull what each of a bunch of colored lasers we're inserting at the end of a fiber at the other end, and then decide what ones and zeros are there. But That's the job of the line termination. The link layer is what looks at these bits and tries to see patterns. So if you see a stream of bits coming by, how do you know where the beginning of a frame is? Like, the bits are all ones and zeros. None of them stand out and raise their hand and go, like in the Olympics where the next country has somebody holding the flag and say, oh, okay, among all these athletes, I know the next country starts here. That doesn't exist. So you're going to have patterns that you've agreed to ahead of time that you'll send, and only when you see that pattern will you know that you're at the beginning of a frame, and then you can begin to decipher it based on that. Once that's done, you've sort of decided whether you have a good frame or not. You've checked its error code. You've received the entire frame. You've thrown it out if it's corrupted or you think it is. And if it's not, you peel off the layer 2 and you hand the layer 3 datagram to this decentralized switching module inside the input card. And that's where you're going to have the whole table where this card can look at the destination IP address that it now sees in this datagram and look through its list and see, do I know where to send it? And then the switch fabric it works with has the task of getting it in line in this queue. That's what those red bars are. They're packets lined up waiting to leave this input card and get across the switching fabric. They're waiting for their turn one by one on the fabric, and they want to go to an output card at the other end. All right. So again, the internet generally just looks at one thing. It looks at the destination IP address. Out of all those fields in the IP header, it's the one field that it generally looks at, and that's traditional. So there's lots of reasons why we would like those routers to look at a lot more things besides just the destination address, but they won't. So that's another push towards re-architecting the way this works. If I pull the software out of the router that is doing the control plane and move it into a data center where I have a lot more compute capacity available, maybe now I got the ability and the time and the capacity to start using more sophisticated algorithms that take a look at other things inside that header, like which port it arrived on, or who sent me this packet, and is this destination one that I don't wish to forward packets for at all right now for whatever reason. So that's more of a generalized forwarding function, and that's something that you might try to implement. Okay, time to shift gears. We now need to talk about a little more detail in destination-based forwarding, but we're going to look at a routing table. So this is tedious, so I'll warn you right now, if you haven't had your second cup of coffee, run and grab it, because you're going to need it to kind of go through what we're about to do. So I'm going to pull up a new blank chart, and we're going to look through this a little bit together. All right, so this is a routing table, better known as a forwarding table, and it has 3 entries in it that match for specific ranges of IP addresses, and then it has kind of a leftover one at the end, which we should really call it what everybody in the world calls it, which is a default route, not an otherwise route. So I'll go ahead and change the name of that. And the way this address range works is you specify a pattern that you're looking for an incoming packet's destination address to match. So the idea is if I receive a packet and I look at its destination address, and its destination address starts with 11001, then I can take a peek here and see, all right, well, it could match this one, for example. These start with 11001. So if it was as simple as that, then what am I supposed to do with this packet? It says send it out of the router on link interface 0. So let's take a closer look at these ranges of IP addresses. What the first one shows us is, and let me pull up the correct tool to do this, and I want the rectangle, and I want the color gold, which is right here. Okay, so this is an IP address. And what this first row is saying is, if you send me a packet and it matches an IP address anywhere between this address and this address, then let's consider it a match and send it out link interface 0. So what do you notice about these two addresses? What I notice is they're exactly the same as each other up until this point. And after that point, it's all zeros up to all ones. And you and I know, knowing a little bit about binary, that all zeros to all ones is every possible combination, every binary bit. So what they're saying is, if it starts with what's in the orange box, it doesn't matter what bits are past that, because I'm telling you, no matter what those bits are than the blue box, anything from all zeros to all ones, I am the row in the routing table that you want. So I want you to match against all those. So what I really can do is ignore these last bits and just pay complete attention to the first 8, 16, 21 bits. So I'm going to look at the first 21 bits, and if they match my destination address in my packet that showed up, then I will send it to link interface 0. All right, so far so good. The next one, somewhat similar. They match, whoops, I got to turn my rectangle tool back on. The second row matches, like the first one did, up to a certain point, but this one matches further. Right? This matches the first 24 bits. And so what they're saying on this one is, I don't really care what the last 8 are, regardless of what they are, I will match between these two. Right? Make sense? So if you show up with the packet and it matches these first 24, then that's what I want to do. So here's the problem. The problem is up to the first 20 bytes, or 20 bits rather, they both match my packet. So in order for me to figure out if it's the first one or the second one, I'm actually going to have to continue looking as far as I can into the packet and stop only when it doesn't match anymore. That's the task of looking for the longest matching prefix. The last box picks up and shows us some matches as well, but this one stops here, goes back to being a shorter one again, because after this point you'll notice the bits are different once again, and they go from 0, 0, 1 up to 1. So this one's strange because it's not the entire range of all zeros to all ones. So I can't say anymore that if I just match the first 21 bits here, then I don't care what the rest are. That's not going to work. So what am I supposed to do? Am I supposed to continue looking here for every single one? No, and here's the saving grace for this. One of the things you might have noticed as we went along is that this range covers everything that starts with these 21 bits. If I add 1 to this address here, the next binary number after this one turns out to be this one. That will never happen in reality for you in a real routing table. But for our example, to teach this, it does. So these blocks of IP addresses are contiguous. So where this one leaves off, this one picks up. And you can see it. This goes from zeros to ones. You add 1 to this, it's going to carry. These are all going to turn into zeros. Going to carry the 1 out, and that's exactly what I'm looking at here. So this one goes from here all the way up to 1s here. If I add 1 to this one, I'm going to get all zeros, and I'm going to carry a 1 out to here. And that's exactly what this number is here. So I can do sort of a no matter what's left over, regardless of how unlikely must be the answer, kind of a Sherlock Holmes sort of rule. I can first try to match this one, and if my destination address in my packet matches these first 24 bits, then I will send it out link interface 1. And I will be confident when that happens that I will have gotten every combination where the 22nd, 3rd, and 4th bits are zeros. There's no other binary numbers where the 22nd, 3rd, and 4th bits are zeros that start with these 21 bits. I've exhausted them all right here. So therefore, I can ignore the 22nd, 3rd, and 4th bit from now on. Anything else other than 3 zeros in these locations is going to get matched to this one, because this one picks up one past this. So here's my first one, and it goes all the way to all 3 ones. So the zeros were taken care of here. Everything else was taken care of here. So I don't have to worry about figuring out exactly what the pattern is. All I need to figure out is that it's not this one. If it's not this one, and the first 21 bits match still, but the next 3 aren't zeros, then it must be this. So that's another reason why we first look at the longest matching prefix we've got. And if it doesn't match that one, then match the one that's shorter. And ignore, that's how you can get away with ignoring what's left. Right? So it's kind of brilliant, a little subtle, but hopefully you were able to kind of grasp the concept there. Right, so to continue on through our slides, we'll now look at exactly what we talked about. We've noticed they match. There's full ranges between the two, and these things, don't match here. And so this is a little bit of an exception. I don't like the way they kind of drew it. This is not the way the route would end up. The route would stop after the 21st bit. So if we actually go to the routing table that results, you will never have from here to here, from here to here, from here to here. You will have, if it matches this first string of bits, I don't care what the rest of the bits are. And as you can see, the last one is as we drew it over here, the last one is shorter. It's not as the book implied here, where you continue to look at all 24 bits. You do not. You look at just the first 21. So because these two match, for the first 21 bits, you've got to make sure if it also matches the next 3, you better go here. All right, so let's take a look at a couple of examples. Here's a destination address. It starts out like this. Where do I send it? Well, it matches all 3 for the first 20 bits, right? All 3 of these have the first 20 bits the same. That's here. And then the 21st bit, what is it in our packet? It's a 0. The only one that matches that is here. It goes over link interface 0, because it's the only row that had a 0 in this position. What about the next one? It has a 1, 0 in blue. So this one is 1, this one is 1, 0. This one is 1, asterisk. That also matches 1, 0. The asterisk means it'll match anything. So I need to keep going a little bit. I don't know if it matches this one yet. It's 1, 0, 0, 0. That matches this one. All right, that's longer than this one, so this is a better match. I will send it out over port 1, for example. All right, so the Cisco Catalyst has a million routing tables, and here's where we talk about how the sort gets done. We have a different type of memory in these input routing cards than you have in RAM. It's called TCAM, or Ternary Content Addressable Memory. Normally for memory, what you do, send every element in your memory the address. So they all get to see this 32-bit address, whatever your architecture is, and you ask them, whichever one of you has this address, raise your hand and dump your contents out onto the data bus. So they all have access to the data bus, but only the one who matches is going to send their output out that way. So that's the way normal memory works. With TCAM, it's kind of the opposite of that. So what TCAM is going to do is basically say, all right, I'm going to send you the data, and everybody take a look at the data and figure out who among you has something that matches this. And if you do, raise your hand and send it out over the address bus to tell me kind of what link interface I should send. It's not exactly reverse. This address isn't exactly the same as this one. But what you're doing is getting all of these elements to search simultaneously for whoever's got a match. So everybody's going to match any address that starts with 1. They all have that. They're also going to all match any address that starts with these 8 or with these 16. So you need a little bit more sophistication. You need whoever matches the longest to raise their hand. So everybody that matches, they may all answer, and then you may need something here that picks the longest one as the winner. Right? So you're going to look simultaneously in all locations of memory at the same time in one cycle and figure out who's got the routing entry that best matches this destination address. There's other types of systems that use this memory now as well, machine learning systems and some GPU-related systems. So there's a lot more competition for the memory, and it's made everyone's lives miserable for the past 5-6 years because no one can ship equipment fast enough. Everyone's waiting on memory. The tsunami in Japan also had an impact on that as well. Different kinds of switching fabrics can be used to give the input cards access to the output cards, but the basic idea is to send it along. In the old days, like dinosaur days, you would receive a packet, you would send it into RAM, to the program, to the routing algorithm, and you would ask it, where do you think I should send this? So you'd all put your feet up, and you'd have soft drink, and you'd look around for a while. And you had all the time in the world because the networks were really slow, and the software could run faster. Not anymore. That can't happen anymore. So now what you have are things like buses, where every input card and output card are on the same single shared bus. So only one person can use it at a time. So it has to be super, super fast. And the book loves to use Cisco examples. These are not my bullets. They're the author's bullets. On a Cisco 5600, it can handle 32 billion bits a second on that bus. So you divide that up over your input cards. If you have 10 input cards, and each of them can run at 3 gigabits per second, for example. Okay, but you're waiting on bus. Then there's an interconnection network where if you have sometimes combinations of transmissions that can happen. So I can see a couple here, for example, where I may be able to run something from A to B at the same time I'm running C to D, et cetera, because they don't touch each other. So you can imagine that going on in this diagram here. And the Cisco 12000 implements this type of switch. It can do 60 billion bits a second. One of the problems that you'll have in these types of situations is people that show up with packets that are all vying for contention to reach the same output port. So here's an example of where I've got 2 oranges, 2 reds, and a green. How should you organize these things on a scheduler? How should you decide who gets to go next? So one thing you can do, and see if I can work a little bit of magic here. One thing you can do is decide, I'm going to draw this myself. I don't need any help. Can I have skills? All right. So you've got this problem. These things show up, and you've got to decide how you want to send things across. All right, well, you could let this guy go first and let this guy go at the same time in round 1. And this guy does nothing in round 1. And then on round 2, this guy can go, and this guy can go, and this guy waits. And then finally in round 3, he can go as well. So it takes 3 rounds in this one to kind of get that stuff done. Okay, you could do that. The other thing you could choose to do is let this guy go and let this guy go at the same time. And that will be what happens in round 1. And then in round 2, you let these 2 guys go. Maybe you move this one to the front and let him go in advance. Maybe you let this guy go in round 2. So you have some choices you can make. And what you're going to find in some of these examples, and I'll give you a homework problem on this as well, is sometimes you're going to figure out the best thing to do is to switch the order of 2 of your elements. So, for example, what we could do here is switch the order of these. He goes in round 1, he goes in round 1, and he goes in round 1. And then in round 2, he goes, and he goes, and you're done. You cut a third out of the time it takes to get things finished. So the input cards actually have a lot of intercommunication and visibility with the switch fabric that they need to have. When you have someone like this poor green guy who has to wait for somebody in front of him to clear out of the way, this is called head of line blocking. And it's particularly bad when, in that first example, I let this guy go first and he couldn't do anything. So nothing's happening, and the green guy goes like, I can see my output port. It's wide open. Why won't you let me go there? So that's an issue not just in networking. This exists in In software as well, you can have head-of-line blocking in queues in software where you've got multiple people trying to use a certain component of a software routine, and they can't get to it because somebody else is waiting on a resource. You also have this in computer architecture all the time. If you took that class from me where somebody's waiting to get into the ALU because somebody else is waiting on a memory output that happens. So you'll have blocking all the time. On the output port, you've also got a buffer, and you need a really good scheduling discipline to choose among the datagrams who's going to get transmitted. You can choose to vary the order based on size and time and bandwidth. One of the most critical things you've got to do is decide who's not going to get to go, who's going to get left behind, who's going to get dropped. And if you're going to drop a packet, I would argue for you that it's better to drop it as soon as possible instead of waiting around and having it take up space and processing for a long time. So if you want to implement prioritization in a router, give priority to voice packets or data packets, for example, then you can implement scheduling routines. At the opposite end of the spectrum are rules that prevent carriers from doing exactly that because the FCC wants them to implement net neutrality, for example. So here is the place where that gets done. It's in this slide in that type of card. All right, so we talked about output port queuing already, and when you have things up, there's actually an RFC that tells you how much router memory you need to have, how much buffer you need to have, and it's basically the link capacity times a typical round trip time, and say a quarter of a second. There's a more recent variation to that, which says if you've got a certain number of flows, a certain number of TCP streams going on, then you can cut down on that buffering a little bit by dividing it by the square root of the number of streams. Right? Scheduling mechanisms, you've got mechanisms to decide who am I going to drop. Do I drop the last guy that showed up if I start to get full? Do I drop somebody at the very front? Do I randomly drop people? Do I prioritize the packets and then drop the low priority ones instead? This turns out to be a big issue. So in this slide, we see a couple of different diagrams going on. I've got red and green packets arriving. They're in my queue, and I choose to send the red ones first and then send the green ones. And then maybe there's another red one that shows up, and maybe there's a delay, a gap in time now where a green one shows up. So you've got to implement these things. One of the things that's given a name to is this sort of round robin idea where you sort of scan among the various class queues, and this is sort of like a 1 for me, 2 for you, 1 for me, 4 for you, and you can implement prioritization, but you have to be fair. So most of the schemes that you will see implemented in routers implement what's called weighted fair queuing, and it's a generalized version of this round robin where just because the red packets are the top priority doesn't mean you starve the green ones and the blue ones off of the network. It's unlike that video thing that we showed where you do sort of video processing where you may divide up your image into squares and send all the things that change the most first, et cetera. This is one where you do need to give every queue access to some amount of its buffer, right? So you got to give everybody access to the network. Okay. Continuing on with the network layer plane, we'll take a little bit of look in what's going on in IP here, and then we'll get out of here. So the network layer is actually a collection of programs. It's not just IP. There's lots of things that run in here. All of your routing protocols run inside the network layer. They build these forwarding tables, and the IP protocol is constantly referencing that forwarding table to figure out, where do I need to send this thing next. And you push some of that responsibility down into the line card. But there's other things that go on here, like ARP runs in here, and ICMP to do things like ping and trace routes run in here. You've got some other protocols that'll pop around in here as well. This is where an ARP table lives. This is where your MTU table lives to tell you the size of frame. That's the biggest one every network link can handle, and so forth. All right, so here's my IP datagram. As always, we draw it 32 bits wide, and you have a version number that tells you, like IP version 4. There's a header link that we'll take a little closer look at, and it doesn't have enough bits to really specify exactly how big the header is, so we just use a few bits, and we make your header a multiple of that number. And I'll talk more about that later. Type of data, how many hops are left. when we run a trace route, we intentionally send packets that will expire so we can force a router to complain back at us. And it's like, aha, now I know who you are. You complained at me. Should teach you better to complain. So that's a TTL that you may have heard of before. Upper layer protocol would be like TCP or UDP. The total length of the IP datagram, you'll use this minus the header length to know how much TCP or UDP data is in there. The TCP header doesn't have a length field, for example. Okay, so you've also got things for fragmentation and assembly in case your program and TCP handed you a packet that is too big to fit on this network. This network wants smaller packets. If that happens, you have to fragment, bust the packet up into pieces. There's also things like options in here. You can ask routers along the way to please put a timestamp in, like somebody, you might ask them to put a stamp in your passport so you know you can prove you've been there, et cetera. And then below that is all the data. So how much overhead is in a packet? TCP has 20 bytes of overhead, and IP has between 20 and 60. 20 are required, but you can have up to 40 bytes overhead on top of that. So there's quite a bit of data that needs to get sent just to allow the data to get sent. So if you're running Telnet and you're sending packet at a time, which is the way Telnet traditionally worked, that can be tough. That can be rough, right? One packet at a time, you're sending 40, 50 bytes worth of overhead for one packet of payload. All right, let's wind up by talking a little bit about fragmentation and reassembly. It's possible when your packet reaches a certain router in the network that it discovers that the route it wants to take is over a technology that cannot handle a packet as big as what you gave it. ATM is the perfect example. It handles 53-byte packets. You will not normally send packets so small out of your computer. So at some point it's going to arrive at a router along the way, and it's going to have to get busted up into pieces. So the value that we are consulting in a table inside the router that alerts us to this fact is one that contains a list of maximum transmission units, otherwise known as MTUs. And you have an MTU on your network interface as well. You can open up your network configuration, and in my case on a Mac, it's under the advanced settings for hardware, and here it is right here, 1500 bytes MTU. If I want to change it, I can make it something smaller. So if your network is not acting well and it's dropping packets and stuff like that, one of the things you can try is just shrinking the size of your packets. Smaller critters have a better chance of getting through the space that's left than big critters do. Right? So you can try changing that, and you have the ability and the permission to do that. So in our case, I need to divide my packet up into 3 pieces, and all 3 of them have an IP header because they could all split and go different directions now, because they're being routed, right? There's no guarantee every packet takes the same route. So they have to be full-fledged, card-carrying IP datagrams all on their own. So that's what the orange represents at the front. There's a header, a full-blown header on the front of every one of these. The only thing you may leave off are the options, the optional stuff off the second, third, and fourth one. They take their journey. They may go different routes. There's no guarantee any router along the way is going to see them all. And they arrive at the destination host, which is where they get reassembled back together. And the host is good at recognizing that they're fragments and putting them together. Maybe they show up out of order. It'll keep space. And when everybody's seated again, then it assembles it back into the original datagram and hands it to the program, hands it up to TCP in that case. So that's called the reassembly area. All right, so here's a 1500 byte MTU network that I'm showing up at a 4,000 byte packet. Not going to work. Going to have to split it up. So I can handle 1500 bytes, so the total length is 1500, but 20 of that needs to be header. 20 of that's going to be IP header. So how am I going to divide this thing up? What I'm going to basically do is have 480 bytes in my data field and 20 bytes of header. Have to have the header. So if I take my total, I've got 4,000 bytes minus 1480. And that leaves me with 3520, something like that. And then I've got another 1480 that I will send after that. Whoops. And then the last one I don't need is, whoops, what happened to my last slide? Where in the world did the last slide go? That's totally bizarre. The last one didn't need that much. The last one only needed 1,020. So if I do the math right, which I usually don't, especially when I'm like talking at the same time, um, and yeah, so I'm like one off here. So I need 1040, but it's actually going to be 20. So I kind of messed it up, but that's because I forgot to include the 60 bytes for header that I have in there. It will work if I go back and add the 20s in. So here's what you'll notice. Each of these is as big as they can be until you get to the last one, and maybe you don't need that much space. The other thing that's important is to look at what's going on with the flags. So now that I'm fragmenting, I need to turn this 0 into a 1 that says there's at least one more packet after me that you need to assemble to get the whole picture. That's all it means. It does not mean I've been fragmented. So again, what this means is if it turns into a 1, it says, here you go, but you need to continue to listen because there's at least one more packet after me that you need to put together with me to get the full picture. And again, for the second one, there's at least one more packet after me that you need to get to make sure you got the full picture. When you get to the last one, it goes to 0. There is no one more after me that you need to assemble with me to get the full picture. So what's happening at the receiver is it's getting these packets, and it knows the first one, if it arrives in order, it starts at byte 0, and it's 1480 bytes long. It does not know how long the datagram overall maybe is going to be. It just knows this one is 1500 bytes and 20 was header. Okay, great. Another one shows up after this, and how does it know that it goes right next to this one? Well, it knows the length, and it knows it's a fragment. But the reason why it knows it's here is because of this offset. And the offset is a multiple of 8. So if I actually multiply this offset number, which you will find inside the datagram, then you will get this number 1480. So what this basically says is byte number 1480 is my first byte in this datagram. So this one runs from 0 to 1479. That's 1480 bytes. And this one's going to start at offset 185, which is byte 1480, up to 2559, I think. Something like that, right? So 28, 29, 29, 59. So this next one's going to be twice that. So that's how you know to put it. So this helps because if they show up out of order, you know that this one goes in the middle. Just because it shows up first, it doesn't mean it's first. The offset tells you where it goes. So it's possible you may get things in an order like this. And when you are convinced you have all of them together, you send it up. Well, how do you know you've got all of them together? Because there'll be one that has a packet of 0, and you can look from the very first one that had the 0 offset all the way to the one that had the 0 flag, the 0 bit. And as long as you have no gaps in here, you know you've put the entire thing together. One last tidbit on this. There's a serial number that's given to every IP datagram, and it's represented by the letter X in this diagram. Normally, every single IP datagram sent out by a computer, regardless of what program it's from and regardless of who it's going to, they have incremental serial numbers. When you fragment, the fragments all keep the same single serial number as the parent did. That's how you know when fragments are showing up that this fragment belongs here, but this fragment belongs to this stream, and there's a third set of fragments that you've got dealing here. You know these are separate from each other because they have different ID numbers as well. All right, that's what we've got time for today, and I will see you guys back in class on Tuesday morning. Sorry, I'll practice my addition and subtraction. Bye, everybody.